Ladies and gentlemen, today I have the great honor of introducing a renowned researcher and pioneer in the field of complex probabilistic modeling. Please join me in extending a warm welcome to Professor Marta Kwiatkowska from the University of Oxford. Her talk will delve into a very intriguing realm where artificial intelligence and causal reasoning intersect. With her extensive expertise, she will shed light on a very critical element of Bayesian networks, namely their resilience in the face of causal interventions. Throughout her career, she has consistently pushed the boundaries of formal methods and probabilistic modeling, and her seminal work has led to fundamental advancements in the analysis and verification of complex probabilistic systems. Among her notable contributions, she pioneered techniques enabling the rigorous analysis of Bayesian networks and the response when the causal structure of those networks is changed. Through her groundbreaking work, she developed novel formal methods to provide provable guarantees on the robustness of such networks. However, her research had not only advanced her theoretical knowledge. Indeed, she led the development of a world-renowned model checker called PRISM, and that model checker has numerous applications in the real world. Her work has implications for fields such as autonomous robots, synthetic molecular devices, and healthcare. And any field where reliable decisions are very critical has proven very useful for this. She made significant contributions through numerous publications. Her research is widely cited, and she is a recognized leading authority in the field. So today we have the privilege of having to hear from her directly as she shows her insights on provable guarantees on the robustness of Bayesian networks to causal interventions. And I invite you all to engage in what will be undoubtedly a very exciting talk and a discussion with strong theoretical and practical connections to our lovely community. Please join me in extending a very warm welcome to Marta Kwiatkowska.
Good afternoon, and thank you for this introduction. I wanted to start by saying that it is really great to be back in a real lecture room with a real audience. After years of doing these keynotes online, it's not the same experience from my side, it's not just from your side. And the second thing I wanted to say is I'm very grateful to the organizers for inviting me to give a keynote in this community. This is because I have been working with probabilities for probably nearly 25 years, maybe even more. And of course, because these probabilities are estimated, they are imprecise probabilities. So I have a feeling that there are very valid connections between my work in the past and my more recent work to this community. And I hope that with this presentation, I can introduce some problems and perhaps stimulate more interactions. So what I have focused on in this talk is the intersection between what the imprecise probabilities community is doing, but also with the strengths of computer science, theoretical computer science, in particular model checking, which relies on logic and techniques that derive from logic, symbolic techniques. But, okay, let's start with the context. These days, we have AI in decision-making. It is being made in biometric face verification. It is being used in autonomous driving and, of course, also in clinical diagnosis. And by AI, of course, AI has a long history. There is AI based on logic, but what people mean in this context is data-driven AI. And the question that has been occupying me ever since I started working with engineers on a project that involved machine learning and neural networks is, should we worry about AI decision safety? And this is because the community has already known, machine learning community has already known since 2013 that neural networks are unstable to adversarial perturbations. So in particular, this example here is an image of a dashboard camera, image, and a award-winning neural network there. If you perturb that image by changing just one pixel, and the image was classified as a red traffic light, the classification will change to green. This is what we call instabilities, and also, potentially catastrophic decisions made by neural networks. Now, what I'm showing you in the middle is a physical attack. That was actually the attack that was made on a Tesla, and the attack involved just extending this digit 3, and it resulted in the car misreading the sign. And what I'm showing you there is a real traffic sign in Alaska. Okay, right. Well, so because of these instabilities, there is much effort that's being put into local robustness guarantees against perturbations that are bounded. The idea is that if you bound the power of the adversary, then perhaps you can ensure stability, invariance of decision-making with respect to these bounds. But we also need provable guarantees. And this is something that I've been working on for many years now. Provable guarantees via model checking. So I'm showing you an example of what model checking, and we call it formal verification, automated verification as well, does to software. So you take a piece of software and you can build a model of that software automatically, or perhaps, from a standard. And that model is either a transition system with states and transitions between the states, can also be augmented with probabilities and other information such as time, etc. So modeling is a rigorous abstraction of the software system, that's the one that's perhaps sitting in making this AI decision. Verification is a proof that the model satisfies some specifications, saying no catastrophic change, to the decision. But what we also look for is synthesis. So we want to synthesize a model or a strategy that's correct by construction. And the focus is on algorithmic techniques which are implemented in software. Now, more recently, I've started extending these model checking techniques towards neural networks. But I'm not going to talk about that side. Now, in my work, I have focused not just on model checking, but what we call probabilistic model checking. And this is proofs, but run in a computer, for systems that have probabilities in them. Why? Well, because stochasticity is everywhere, and these decisions are often based on probabilities, for example, in randomization, or perhaps in some kind of modeling where we need Monte Carlo techniques. So for these, what we need is quantitative probabilistic guarantees, and there are natural properties, reliability, safety, energy usage, resource usage, etc., that are expressed using probabilities and perhaps some other quantities. And within this, my focus has been on these automated tool-supported methodologies with which you can build a model, okay, and I'm talking about models that can have millions and billions of states, but then you want to run a verification against some property, and for this we have developed this model checker Prism, which was mentioned, and that one started with Markov chains, moved on to Markov decision processes, and now we are working with multiplayer stochastic games and even equilibria. You can have a look there if you are interested. And I'll just show some examples of systems. These are actually outside Prism, but there have been tremendous successes of this probabilistic model checking, probabilistic verification. This is an example of a pacemaker. This is an example of a DNA folding system. So I'm really talking about a huge system, but I'm also talking about a very abstract model of that system that was used to predict the folding. And this is biometric, this is ECG-based biometric. So there have been many successes. And now reflecting on the connection to this field, I wanted to highlight that the advances in probabilistic verification and in verification model checking in general are due to a large extent symbolic representations that are derived from logic properties. And this means that even though verification is intractable, because the actual problem often involves checking all the states, and the size of the state space is exponential. That's the very definition of intractability. What we can do is to look for representations, and in this case, I'm showing you a representation called a binary decision diagram. In fact, they are called reduced order binary decision diagrams. These store as much information as this and as that, but they are much more compact. They are actually canonical for a given variable order, okay? And on top of that, the structures that underlie Prism also extend to representations for probability matrices. So if I have a probability value here in this function, you can then have a multi-terminal where you don't have just 0, 1, but you have real values, any number of real values. And these support efficient matrix vector operations and value iteration and approximation, etc. So this is just one example of a symbolic data structure. There are many more. SAT SMT, they were mentioned this morning. SAT was certainly mentioned this morning. The reason I'm mentioning this is because there is a connection between the work that I'm going to talk about now and this, okay? So a lot of the success is coming from exploring these representations and looking for algorithmic techniques. So this is not in the problem. If the problem is intractable, there's nothing that you can do other than look for representations and tricks, algorithmic tricks. So this lecture is continuing my search for these representations that can support tractable inference, okay? So from shifting now towards inference, and ideally also towards learning, which I will not have time to talk about, but I will point you to some work. But rather than focusing on input perturbations, which can be seen as artificial, because you take a neural network model, and then you identify some perturbations that may perhaps throw the model. But this is not a realistic model of what can happen in a system, because in a system we have to take into account the data generating process. So we have to consider the environment that produces these images. Okay, and because of that, I've switched to Bayesian networks. So they are directed acyclic graphs of random variables, and I'm showing you one here from a typical insurance case study. And the idea is that if you have this environment, then before you deploy it, you want to stress test the, say, insurance policy to check whether the policy can be gamed. So, we know that distributions shift. There was a distribution at some point, but when the policy is introduced, say there could be, a premium, and if the company starts offering reduced premium to people who take a class, then we know that people may see this and may start gaming the system. So the idea is that the insurance company can then explore these different environments, different distributions, different intervened Bayesian networks. But how do we express plausible distribution shifts? Because we can't obviously consider all distribution shifts because that's not realistic. So for that, we define the interventional robustness problem for Bayesian networks. And the aim is to quantify the worst case performance over a set of distributions. And in order to model the plausible distributions, I'm going to say that the conditional probabilities are actually causality assumption. Someone, to start with, gives me the information that this is a causality link, but I will later tell you how you can actually learn, how you can do causal inference, okay? But for now, we are assuming that these conditional probabilities are causal assumptions. But of course, these probabilities are also imprecise. So later, what we are going to do is we are going to extend Bayesian networks with Credo sets, but also in this context of causal adaptations. And what we want to do is we want to, the problem itself is intractable. We know it's exponential for Bayesian networks, but we want to find a representation which will ensure a tractable inference algorithm, and by tractable, I'm going to mean polynomial time. And I also want to have provable robustness guarantees, but something has to give in, because, of course, the problem is, so what I'm going to say, my proof is going to be some bounding. Okay, I'm going to bound, so it will be an approximate problem. Right, so what we are doing here is, well, I take as context this environment. It's a Bayesian network that, say, perhaps some insurance company has developed here. But then what I'm also, and it's discrete, I'm also taking a decision function. So this could be a neural network, okay? But that neural network uses information from the environment, okay? So there is some sharing of data between the Bayesian network and that decision function. And what I'm going to define is interventional robustness, which is the worst case performance of this decision function under these causal interventions. And how I'm going to define, there are two types of causal interventions that we are defining. And the easiest one is just to modify the parameters, and that's what this example is showing you. So modify the parameters. And of course, that means that if I have a Bayesian network, then I need to, for this specific set of interventions, I want to then compute worst case performance. I've omitted the definition, but you can do something similar by allowing the change of structures. So I can allow interventions by selecting a subset of the variables. And because I know that conditional distributions in a Bayesian network are independent by the design, I can intervene on them independently, okay? And this is what I'm going to do. So I have these parametric and I have structural. Okay, and the definition of the problem is simply worst case. This is the maximization over the set of all the possible networks that you obtain by intervening on that set of variables. Okay, so, theoretically, there is, nothing special here, and I'm showing you for the a little example here, but note that this is different from sensitivity analysis because it's a global property rather than a local sensitivity analysis that you might want to perform on a single parameter, okay? So this set of interventions is all interventions which only change the mechanisms, and there could be parameters, but they could also be the context, so the parents, the causal links can change, for example, for the structural interventions. So they only change the mechanism of a subset of the variables. Okay, so that's the formal statement of the problem, and what do I do? So this is where I use structures that come from computer science, and in spirit they are similar to binary decision diagrams, the OBDDs, ROBDDs that I showed you before. So I have a Bayesian network, and separately I have a decision rule, okay? So for a Bayesian network, you can go to a logic encoding, Satin formulation, so you can obtain a BN that's only for discrete, as I've mentioned, and this side was formulated and implemented in a group of Adnan Darwish some years ago. And this aspect is what we are adding. So we can take a decision rule. As I said, it could be a neural network, okay? As long as you can encode it, so you can discretize it, and you can encode it as a logic formula, then you can compile it by effectively taking a conjunction, because I will say, later why not. And you can, on that arithmetic circuit representation, you can run my algorithm. Okay, so why arithmetic circuits? So these are circuits that were introduced as a representation for distributions some years ago, and this is a rooted directed acyclic graph, which has as internal nodes plus and times. We want to focus on distributions. And as leaf nodes, it either has indicator variables, which indicate the discrete value of each variable, and another leaf node are parameter variables. So here I'm assuming in this encoding it's binary, x and x bar is the complement of x. Okay, so I have a Bayesian network and I'm mapping it to this kind of arithmetic circuit. Now the advantage of that circuit is that I can now run marginal inference queries. Why marginal? Because I'm intervening on a subset of variables. Marginal inference queries in linear time. Okay? So, you know, as I said, I'm not tackling the full problem because it's prohibitive complexity. I'm looking for representations that will, under some assumptions, allow me to do this. Okay, so what we do is we do joint compilation of the Bayesian network and the decision function. So we effectively reduce them both to logic formulas and compile them jointly. And this is because if you do it naively, you'll have exponentially many inference queries. My student has actually tried it, and it just doesn't work. So he ended up extending it to this. Right, but that's not everything. Another thing is because what we want to do is then we have this representation. Okay, we have a representation, but the representation is for the Bayesian network with the decision function. Now I need to be able to change, you know, to operate on this representation, to look at all the possible, plausible causal interventions. Okay, now for that I need to match the structure of the AC to the interventions, and because the interventions are causal, I cannot reverse the causal links. So I actually have to assume, and again this is similar to ROBDs, I have to assume an order, topological order on the variables. And I exploit this in the compilation. That is so that any of the intervened variables, a parent of any intervenable variables does not appear in a subtree of a plus node. Okay? So this is a restriction, and the reason I'm doing this trick is because I want linear time in the size of the AC, which admittedly is larger than the size of the BN, but I want linear time inference. Okay? And then what do I do with that? Okay, so now what I want to do is I want to compute the maximum, okay, the worst case probability. So I want to maximize it. And I have this kind of circuit. And if you think about it, we know that inference on this is linear. If you replace every plus node with a max node, I still have the linear. Okay, I'm not doing the summation. I'm in linear time. I'm just getting a bound. I'm getting an upper bound. Okay? So I went from a Bayesian network to a circuit. I threw in some conditions, and I have linear time upper bounding. Lower bound is also quite straightforward. You can do it by local search. But as I've already mentioned, this is this problem. You can actually show that this problem is interreducible with maximum a posteriori, which I think, as we heard earlier today, is the reductions are polynomial, but the problem itself is NP to PP. Okay, so the problem is still there, but I can do things tractably. And for computational performance, okay, so because we have these representations and they are compact representations, and inference is fast, it also turns out that the bounds, even though they are approximate, because I get an interval around the actual value, they are in practice, they are quite tight. Okay. Right, okay. So that's where we are, but, okay. So while we have provable guarantees. Okay, so the provable guarantees are really these bounds. So we know that the probability will not be above something, and this is guaranteed. And in many cases, this is enough. In an insurance case, it is enough, because then they can fix the medical costs, the pricing of the insurance accordingly, if they know that. But this method allows any intervention or no intervention. So you always choose a subset of the variables, okay? And then, you are allowed to intervene, which means change the parameters or, change the causal links. But you either allow or you don't allow any. And in particular, you cannot consider parameter uncertainty, because the values of the parameters that we've put into an arithmetic circuit, they are sitting there in the leaves, and they are fixed. And we also have, in practice, the bounds were tight for the examples that we have run it, but there are no guarantees. There are no guarantees on the bound tightness. So this is where, a question arose: can we now use results from the imprecise probability community, in particular Credo sets, and combine the method with Credo sets to generalize our problem to Bayesian networks that allow imprecision in the parameters? And in fact, this is what we do. So we take again, a Bayesian network, but rather than having individual parameters, we allow Credo sets. So these are the allowed values of the parameters, and you can think about them as intervals. And in fact, we've instantiated in the examples with intervals or some polyhedra. And with this, we then need to generalize the interventional sets, because we will now have credal distributions, so the interventions have to work on credal distributions. And why do we want to do that? Well, so this is another example. This one is now from the sort of medical diagnosis. Again, what we want to do is we want to bound the probability. So, we want to get away with a bound rather than an exact answer, because the problem itself is of the same class as before and P2PP. Okay? So what do we do? Well, so we take the Bayesian network as before, which has been augmented with the decision function. So the decision function is encoded, in the circuit via a logical encoding, but it can come from a neural network. And now the notation is slightly changed, but this is still in the same spirit. But I'm focusing on E. What I actually mean is, the event that corresponds to intervening on one of the variables in a specified subset of the Bayesian network variables. Remember, the decision function shares variables with the environment Bayesian network. And the problem itself can be reduced to the maximum marginal probability, and this, if we can compute it, this can then be used to provide these quantitative robustness guarantees, but now computed over credal networks. Now, the problem that now I have is that arithmetic circuits are not great at representing credal sets, because remember, they are in leaf, parameters are in leaf nodes, and they are then not, you cannot constrain them. You cannot constrain them easily. So I have to do more work, but now I have to switch to another representation, and this is also very well-known symbolic representation, which is called sum product networks. So this is a representation which is used for probability distributions, and the only difference is that it moves the parameters from leaf nodes to the weights, okay, to the weights of the sum, and because of that, I can now represent Credo distributions by adding constraints, okay, by adding constraints. Right, so I now have a Bayesian network, you know, with Credo sets. I can map it to AC, I can run it, but now I actually need to map it to a sum product network, okay? Because AC, on the AC, the problem just does not admit an efficient algorithm. So what I then need to do is I need to go from the Bayesian network to an AC in the same way as before, and then from an AC I can go to an SPN, but now I need a Credal SPN. Okay, so I have to do some work because there is a challenge, and that is that each sum node in a compiled SPN represents a conditional distribution. But multiple sum nodes can represent the same conditional distribution, okay? So Credo set of the compiled CSPN is strictly larger than the Credo set of the original Bayesian network. Okay? So I can show this by upper bounding. So this is the CSPN, Credo CSPN. Of course, for provable guarantees, for many applications, this will be enough. But, you know, perhaps we also need cases where we need to know whether we can recover, you know, the original bound on the Credo Bayesian network. So the reason the bound is loose is because we've dropped the constraints as we've translated. As I said, there are identity constraints, but we can characterize it. We can characterize it, and we can show this. Okay, so for an order on the variables, you can have an enriched, a modified Bayesian network for which the bound would then be exact. So I can, if I start with a network without this, go to AC, go to a Credo SPN, I get a larger bound, but I can recover that by modifying the Bayesian network and computing that. And, okay, you can reintroduce these constraints, which has not been done, okay, because these are now unconstrained. So you can bring them in, you can recover the exact bound if you want to, but of course the trade-off is higher computational complexity. Okay. Right, so this is where we've got to. And so what has been achieved? Well, we have come up with representations which derive from the logic, you know, symbolic logic representations to really focus on tractable marginalization. That is just one query effectively that we have done, but we have allowed a range of interventions, not just parameters, but also causal interventions, under the assumption that these are actually causal links. And this has also been achieved for cases where the probabilities are imprecise. So, for example, they are just given as intervals. And as I've showed you, it gives us provable bounds, but because they are bounds, they are necessarily approximate. So elsewhere, we have also worked with some product networks, and we introduced Bayesian uncertainty on learning to support structure learning. Okay, so this is to support structure learning, that is how to learn these DAGs, okay, for Bayesian networks directly from data. But of course this supports learning, but if you want to then do causal identification, then that is a separate problem, which is again an even harder problem. You have no guarantee once you've learned whether this is the true causal structure that underlies the data because of hidden confounders. Okay? Now, so far, we have only worked what I've showed you with classes of circuits, which are arithmetic circuits and some product networks. And the question now I'm asking is, are they sufficiently expressive? And in fact, they are not for many problems that we want to express. They are not. And in particular, not for more general inference queries, and they are not sufficiently expressive for causal inference queries. And for that, there is a more recent paper that I just could not fit in, but if you are interested, there is also a PhD thesis of Benji Wang, my student, which should be available soon. And what this is working with is, you can think about it as a generalization of some product networks. Okay, so these are probabilistic circuits. They work like some product networks. They are used as a representation for distributions to support exactly efficient probabilistic inference, but they encode they are just graphs. They do not have the restrictions that some product networks have, DAG restrictions, for example. They are more general. So the classes that I've talked about are not sufficient to express, in particular, arbitrary compositions of operations such as marginalization, exponent, etc. But with probabilistic circuits, Benji has produced a variant called MDNet, which is a more general class, and with that you can compose operations, and you can analyze, you can find sufficient conditions for tractability and causal identifiability of inference using these circuits and a calculus that he has developed. So there are algorithms for tractable causal inference, but there are also results which say that for the full class, this is not tractable. So there will be operations which are not tractable, but you can analyze the specific combinations, and for those who have sufficient conditions that either do or do not guarantee tractability. And there is also learning supported. Okay, so you can learn these structures directly from data. Okay. So that's beyond SPNs, actually beyond, probabilistic circuits. But if I want to return back to the question of adversarial examples, well, what we have is we had a neural network, and it was a deterministic neural network. So it was a neural network which would take an image, dashboard camera image, and produce a classification, say red or green traffic light. The question now I'm asking is this enough? We know that machine learning itself is a probabilistic problem, so we need to be able to somehow take account of that learning process, and because of that, we do not need the bounded guarantees for bounded adversarial perturbations are not sufficient. We need probabilistic guarantees because of the stochasticity and risk that is involved in, running autonomous cars. So the question we are asking here is, can we use uncertainty? So in addition to the classification, this is a red traffic light, can the network also propose, output a measure of uncertainty in that decision? And this can be achieved with Bayesian neural networks. They are neural networks, but they are endowed with a prior on weights. And if you give it a prior, you can then use Bayesian formula to compute the posterior. Of course, that posterior is intractable, because we are now talking about neural networks. So that posterior is intractable. But again, using, say, algorithmic techniques from verification and from computer science, we can make inroads at the cost of bounding, the probability. And there is a strand of work on developing verification probabilistic guarantees, but also lower and upper bounds on the probability of reachability for a Bayesian neural network, for example. And how has this been used? Well, it has been used for a controller, and this is an end-to-end controller. So an end-to-end controller which was trained on simulator data, not real car data, was trained on simulator data. And it's end-to-end because it takes images, and from images produces a control output. So it can be treated as a regression, because you can just take, the steering output, or you can turn it into a classification. But it is Bayesian, so the control decision also comes with uncertainty, and you can use this uncertainty for uncertainty-aware control, and you can, we've done it to do analysis of safety by shifting environments in the simulator from, say, sunny weather to bad weather, and analyzing the decisions of the controller and whether, enough sort of harness is put in there so that there are, fallbacks if the controller is uncertain about the decision. So this is the end, and I just wanted to finish by concluding that I have focused on selecting topics that sort of directly connect to what you are doing, but I have to say that, in my community, there are years and, of work that people have put into these logic circuits. Arithmetic circuits, are new. Arithmetic and probabilistic circuits are only for probability distributions, so in cases where you have probability, but of course for conventional systems, non-quantitative systems, people work with other symbolic representations as well. So I've explained, what the interventional robustness problem is, and effectively what I've showed you is how you can compile it to these variants of circuits, and then what kind of tricks and, algorithmic tricks, but they are backed by hard results, okay, the ordering. So that without changing the complexity, because the worst case complexity of the problem is the same, by using these techniques, you can reduce the complexity of the problems that, say, your client may want to something that is tractable. And also, in presence of imprecise knowledge and distributional shifts, and elsewhere, you can look at how to do learning and how you can compose, for tractable inference as well, Bayesian networks for tractable inference. But, I hope that, say, you've been listening. There is much work that remains to be done because there are a lot of restrictions that we have assumed. So, for example, it's only discrete Bayesian networks. The decision function is also encoded as a logic formula. The set of queries, this is essentially just marginalization. We need more, and structural interventions must preserve acyclicity. That was a condition that we relied on when mapping to ACs, and the same mapping, okay, then that condition transfers to the mapping to SPNs, and constraint reintroduction is not exploited. Maybe in some special cases you are interested in, say, putting in more computational power to get the exact bound, and this is a way to do it. So that's it, and I just wanted to finish with acknowledgements to my collaborators, my students who did all this work.
Thank you very much. I think we have a bit of time left for questions. Yes, Alessandro. Yeah.
I have a question and a comment, very close to the speaker. My first question is, what about doing why don't you do just the same, but within the field of a structural causal model, which would be probably very, very natural? And just to support this question, for instance, Adnan Darwish is working in this direction. During the compilation process, is taking advantage of the deterministic structure of the structural equation. And maybe related, also exactly as what you did with the SPNs, can be done also with PSDD, where they mix the logical part with the probabilistic part.
Yeah.
So.
Okay, so yes, so the answer to that question is in Benji Wang's PhD thesis. Because there, we are looking specifically at causality. I think what I've shown you is a journey, how we started, with arithmetic circuits. And yes, so for example, he has a result about probabilistic sentential diagrams that they are not sufficient. So his class of probabilistic circuits, MD nets, supports tractable inference and supports causal identification for things like the napkin problem, Pearl's napkin, backdoor.
Just let me mention, as we are at Zita, that probably, they are credal, or they are already arguing for a credal SPN, a credal PSDD. So and I think also you can implement with some limitation mappings between credal networks and circuits.
So so probabilistic circuits are not credal. Mm-hmm. So that result on causal identifiability is without the credal aspect. Okay. But you can bring it in. So this is just straight PSDDs.
Okay. Thank you.
They are subsumed by MD nets, and so are, some product networks, so they are subsumed by MD nets. It's a more general class, and there is a calculus with which you can, identify the assumptions for composability, so that the composed operations give you tractability.
Okay, Erik?
So I have a question. Is this working? Yes. So I have a question about essentially the structure of the circuits that you compile to. So when I looked at the slides, they all look like DAGs and not like trees. And so in work that is being done in our group in Eindhoven, what we see is that there's a kind of trade-off with DAGs. You can get much more compact representation, but you lose let's say exactness or well the bound, how well your bound fits. So is there a specific reason why you want to go for DAGs instead of trees, or is that a kind of trade-off you can also make within your setup?
Yes, so the results, the theoretical results are for DAGs, but the compilation relies on the code from Adnan Darwish's group, and I imagine that you have your own compilation code. No?
More theoretical, I think.
I see, it's more theoretical, yes. So the reason, in order to go down to the implementation, you can't do all the implementation work yourself. So we have used the compilation method from Adnan Darwish's group and adapted it.
Okay, any further questions? I do have like a very simple question. So in the kind of work that we do with Credo sets, linear programming is an essential part of that. And I'm wondering, to what extent can you use linear programming, or is that important to these kind of algorithms that you develop, or do they bypass that completely?
Okay, so for these, I don't, unless it's for, some solving constraints, but yes. I think for the ones that I've showed you, it's just inference, so it's a single bottom-up pass. Okay, all right. So that's what I've showed you, but yes. Of course there will be, I think, for more complex queries.
Yes. For Markov decision, what you call Markov decision process, what we call imprecise Markov chains in this community, linear programming is something that we use.
But even for Markov decision processes, you can either work with linear programming, for example, to compute the probability of some events. But instead, you can also rely on value iteration.
Right.
And value iteration is an approximation which doesn't involve linear programming.
Okay.
But when you move to stochastic games, you then have value iteration, and you may need linear programming at individual nodes. So.
All right. I see one more question. From Jasper.
Hi there. Thank you very much for a very nice talk. I was very surprised by the many connections with the imprecise probabilities in your work. I was wondering, when you move from the Bayesian or the Credal networks to the circuits or to the sum product networks, typically you've got an explosion basically of the number of states. If you try, you can have an explosion if you make that transition. And I imagine that the tractability is only like after you've made the move.
Yes.
Do you have ways of controlling that explosion, or how do you approach that?
Well, so yes, you do have. So I mean, when you talk about explosion, the number of nodes.
Yes, exactly.
But that's polynomial for the AC.
Okay.
Yeah, and then yes, tractability is on the size of the circuit.
Yes.
On the size of the Bayesian network. Yeah. But there could be more. I mean, as I said, there could be more. I mean, maybe, what you are proposing. But then the trade-off, so here, if you keep the structure simple, your inference is faster. So the inference is very fast.
It seems almost like it's moving the problem a bit.
Yes, I mean, a lot of algorithmic work is sort of, exploring the trade-offs.
And for the sum product
And
networks?
depending on, sometimes you have to choose the method for the property, and it will be a different method. So maybe if you start talking about other queries, then yes, maybe it would be a different.
And for the sum product networks, is it also polynomial, the move?
For which?
For the sum product networks, is it also polynomial there?
Yeah, because that's a straightforward map.
Oh, okay.
But then you have to compute the constraints for Credo. Yeah, because we do go to some product networks for Credo, so we then have to put constraints for the probability distributions, Credo distributions.
Okay, thank you very much.
Yeah.
Okay, thank you so much. I think we're out of time. Thank you so much. Let's extend the warm thanks again to Professor Kwiatkowska.
Thank you.
And we can, of course, continue discussions over lunch, which I understand is ready and is upstairs. Yeah. Okay, thank you. Thank you.
Okay, thank you. Thanks for the questions.